All right, let's get into it. When you look up at the sun, it seems so constant, right? Just this steady, reliable ball of light. But the truth is, it's a wildly dynamic and incredibly complex star. And trying to predict its every move, its flares, its cycles, well, that's one of the biggest challenges in science today. And it's a challenge that has some very real consequences for all of us down here on Earth. No, really, think about that for a second. What if we had a reliable forecast for solar activity just like we get for rain or snow? Imagine what that would mean. It would be a total game changer for our power grids, for our communication systems, for every single satellite orbiting the planet. Well, it turns out.
That's right. All around the world, researchers are in this constant and, friendly but definitely fierce competition to build the absolute best model for predicting what the sun is going to do next. So for this explanation, we're going to look at a head-to-head showdown between two of these models. So welcome everyone to the great scientific bake-off for forecasting the sun.
Now, to judge any competition, you need a way to keep score. And to figure out which solar model is best, we first need to understand what exactly the scientists are trying to predict. And believe it or not, it all comes down to one single crucial number.
That number is called F10.7. Now, what is that? It's basically a measurement of radio waves zipping away from the sun at a very specific wavelength. The easiest way to think about it is like this. It's like we're taking the sun's temperature every single day. The higher that F10.7 number, the more active, the more energetic the sun is. Simple as that.
So why are we so obsessed with this one little number? Well, because it tells us so much. F10.7 is a fantastic stand-in, or what scientists call a proxy, for the sun's ultraviolet radiation. And that's the stuff that directly smacks into Earth's upper atmosphere, heating it up and messing with everything from radio signals to the orbits of satellites. You better believe satellite operators live and die by these F10.7 predictions to brace for incoming space weather. And here's the best part. It's a super clean signal. Unlike counting sunspots, which can be tricky, this is a measurement we can take reliably, every single day, no matter what.
Okay, so F10.7, that's our target. Now, let's meet the two competitors in our bake-off. In one corner, we've got a model from a team led by Anthony Yates. We'll just call it the Y model. And in the other corner, a model from John Worden and Jack Harvey, which we'll call the WH model.
So here's where it gets interesting. These two models are trying to solve the exact same problem, but they go about it in completely different ways. The Y model is what you'd call equation-based. It's all about solving the fundamental physics equations that dictate how the sun's magnetic field changes over time. The WH model, on the other hand, is more of a simulation. It takes these little individual pixels from a map of the sun's magnetic field and just calculates where they're going to move based on a set of rules. They also have totally different takes on something called diffusion, which is just how magnetic fields spread out. The Y model uses a simple constant rate of spread based on physics. The WH model? It uses a much more complicated system and actually just shuts off the spread completely in really strong magnetic areas. So yeah, two very different recipes.
So how do you figure out which recipe is better? Well, you put them to the test. And I mean a long test. The researchers set up an 11-year-long showdown. They fed both models the daily data and asked them a simple question every single day. What's the F10.7 value going to be tomorrow? And listen, this wasn't just any old 11-year period. It was picked on purpose to cover an entire solar cycle. These models had to perform when the sun was active and winding down. They had to prove themselves during the super quiet solar minimum. And then they had to keep up as the sun roared back to life towards another maximum. They were tested in literally every condition imaginable. So after 11 years of daily predictions, that's over 4,000 predictions each, the results were finally in. The data was all compiled, the stats were run, and a clear, undeniable winner emerged. Let's just start with one single powerful number, 0.98. This was the Pearson correlation coefficient for the Y model's one-day forecasts. Now, for those of us who aren't statisticians, a perfect correlation, like absolutely perfect, is 1.0. So getting a score of 0.98, that is unbelievably close to perfect. It's stunningly good.
And when you put the two models right next to each other, the story becomes crystal clear. You can see it right here. For that correlation score, the Y model's 0.98 just edges out the WH model's 0.96. But then look at the error rate, the root mean square error. Here, a lower number is better, right? And the Y model clocks in at 5.56, while the WH model is way up at 7.29. So on every key metric, the Y model was just plain more accurate.
It's really that simple. The equation-based Y model did a much better job.
Its predictions were a closer match to what the sun actually did day after day for more than a decade. And this was especially true when the sun was at its most active and most unpredictable, exactly when you need a forecast to be reliable.
But in science, figuring out what happened is only half the fun. The real prize is understanding why it happened. So, what was the secret ingredient in the Yaw model's winning recipe? What made it so much better?
This quote from another research paper really nails it. One of the most important things happening on the sun is this process called meridional flow. Think of it like a giant conveyor belt on the sun's surface. And what this quote is saying is that the way the WH model simulated that conveyor belt, well, it just wasn't very realistic when you compared it to what we can actually see happening on the sun.
And this really gets to the two main reasons the Y model came out on top. First, its version of that surface conveyor belt, the meridional flow, was just based more closely on actual observations, which made it way more accurate. And second was how it handled diffusion. Remember how the WH model just turns it off in certain areas? The source paper literally called that a crude method because it's not really based in physics and it can cause errors. The Y model's simpler, more consistent approach, which was grounded in real physics, just turned out to be far more reliable in the long run.
So this whole scientific bake-off, it really shows us how far we've come. We actually have models now that can predict the sun's daily activity with 98% accuracy. That's incredible. But of course, the work is never done. These models are fantastic at the big picture, but they still have trouble with the small local stuff. The quest for that perfect solar forecast continues, pushing scientists to keep refining their recipes, and in the process, deepening our understanding of our magnificent and sometimes chaotic star. It really makes you wonder, how close can we actually get to predicting the mind of the sun?